I was like, I'll go ahead and buy Thanksgiving dinner. So, no, don't think so. Yeah.
Where are they coming from?
Yeah, Oklahoma. Or they might have flown out of Northwest Arkansas. Not OKC. It's either Tulsa or Northwest Arkansas. I don't know which one. It's like 17 hours to drive from Oklahoma. Yeah, it's like eight and a half to Nashville, and that's with 40. It's 9 and change from Nashville to the edge of Oklahoma, the closest edge of Oklahoma. It is far. I've done it a lot, and it sucks. Like, I was in school in Arkansas, Northwest Arkansas, at the U of A, and I'm from Nashville, so I did that drive a lot. But then my husband's family is another hour and a half further than like Fayetteville. So
I drove to Arkansas. It's called Cave City.
okay,
I drove there for the eclipse.
nice, yeah.
That's cool.
That yeah,
My
that
dad has a camera. He almost destroyed it getting the
of course,
little
yeah.
thing. He got cool photos.
That's awesome.
Really bad. Water town.
It's called Cave City. Yeah, it sounds back.
They have one cave, but they had in GPS like a part so we could set up his tripod and everything. It was someone's front yard, and so he was sitting there fishing in this pond. And we were like, "Is this your yard?" And he was like, "No, this is public property. You can be here." It's like, "This is your house. Is I can touch it." Like,
why is your front yard public property? What's happening in this town? Was there any city in the cave?
It's called
Cave City.
Wait, so they were trying false advertising. This is such a small town that they asked us, they were like, well, we're a tourist attraction for, cave
One cave.
tours and everything. And we were like, oh, cool, we'll go online. And they couldn't scrape together enough people to actually go. So we didn't get to go.
Oh my gosh.
We were like, let me make some phone calls. And they were like, do you want to do a cave tour?
No.
I was like, oh my goodness.
Pass. Wow. Well, I'm going to look up where Cave City is. And then we'll know why they didn't call it Caves City. And Sherrod? Was he? Did you do a good job? Awesome. A Midsummer Night's Dream. You know, the Black Box Theater, the theater department put on, yeah. If any of you need to see a Christmas play, December the 18th, 19th, my daughter is cow number 1, which is the lead speaking role. She was like, I'm cow number 1. I was like, cool. And then I got a letter home. It was like, this is a big part. She's the lead speaking role, all this stuff. Like,
What is it?
what?
Moo.
Moo! I'm like, I don't.
Merry Christmas, Moo.
Yes, it's at Somerville Baptist Preschool. She's gonna be mooing a lot, I think. Like all the blocks of lines, she leads them off, so she doesn't have anybody to like cue her, right? She just gotta know them. Like, this is gonna be interesting. My son, it has like a photographic memory, so he could do it no problem. He would sound like a robot, but he could do it. Ellie, I'm not sure about, so we'll see. Okay, so we are in 12.2. We were looking at, I think, is this 12.2 or are we still in 12.1? But this is 12.2, right? Because of the pictures. I think so. So these are the It's okay. I was ready to answer your question. These are steady-state machines or finite state automata, whichever you want to call them. And remember, the initial state has the like start thing. The states are the bubbles with S sub whatever in them. Input variables, those are your alphabet stuff. They have to be coming out of every bubble. You have to tell what this like machine does with this input value. Okay. The language recognized by the machine would be any string that gets it to a final state. The final states are the double circles. Did we follow all of that? Okay, so what are some strings recognized by this machine? 1.
I think we can fit another one in.
Okay.
Never gonna guess right seconds.
No!
Sorry, one.
Yeah, so this would be the regular expression would be a 1 star. Are we fine with that? Reg X 1 star. And then the to like describe it in words, it's any string of ones. Including none, because just starting and doing nothing will put you in that final state. Cool? Okay. Bless you. All right, number 3. Number 3. Some strings recognized by this machine.
Just 1 and 0.
Yeah, that's it. Just 1 or 0, 1. Yep. I'm not going to describe that in words. Is that fine with you? Okay. Feel like that's done. All right. Number 4. All right, we got 2 final states on this one. How do you get to that first final state? 0 star, good. Mm-hmm. How would you get to that second one?
And then 0, 1 star.
Mm-hmm. This one actually has the 0 star in the front too, because you could do a bunch of zeros and then leave and do a 1 and then a 0 and then a 0 or 1 from there. That is a lot of things happening there. One of those is a bar, one of those is a... I don't know how to do this. I wish I'd used A's and B's instead of zeros and ones. Huh?
Like the one, the little slant.
There we go. Okay. Are we fine with that? Okay. Ooh. The ones are a trap. If they happen before 2 zeros anyway. Zero, zero, and then 0 or 1 star. So you got to do 2 zeros to start with. The way you would describe this would be any string of zeros and ones that starts with 2 zeros.
So why does it have to start with 2 zeros instead of going to
Well, this says if you start with a 1, you go to the trash. Yeah. But if you start with a 0, you're okay. But if a 1 comes next, you go to the trash, and you can't come out once you get to the trash pile. So if you do a 0 and then another 0, you're fine. You're in this final state, and then you can stay there by doing any strings of 0s and 1s. Yes, ma'am.
Well, if you learn this, you could teach discrete math.
So in computers, there's zeros and ones with programs that being very closed, and space is being defined. So you have open states and closed states.
Yeah, we're in the computer science section. And then this is how machines like operate, right? You do one thing and then you do another thing from there, right? Every machine operates sort of like a what do you call those diagrams?
Oh, like, I know what you're talking
Like a
about.
flow chart.
That-
Like a flow chart. Every machine operates sort of like a flow chart. You start here, these are your choices. I always use like the coffee shop as an example, which is a great example for you. Like I'm in a coffee shop, I gotta first choose if I want the barista to grab a hot cup or cold cup, right? And then what size of those cups, and like, you know, like you want the customer to say things in an order that makes sense to you and how you need to pick the cups, right? And so like, you know, it sort of breaks your machine for them to order the milk first when you've got to pick the cup to write on first, you know? And so, like any machine that functions like a flow chart. You got to make this choice. Once you make this choice, you can make a different one, the next choice, things like that. So, and like, yeah, closed states or open states or whatever in a machine allow you to keep going or you're stuck. And like this one, you're, you know, this is a trash pile for this. Your code would return some sort of error or whatever. This would be like, I'm imagining that this is sort of like a for loop or something, or an if then statement. Let's go with that. I said if then, like if else. Sorry, that's what we call it in computer language. So it's like if this, go to S1. If not, if else, then go to S3. And so like if you're writing a big program, somebody puts this in, okay, then it takes them to this step. But if somebody gives you this input, then you know that puts them over here or whatever. So that's really like baby down version of what big picture thing is going on with machines or programming codes. Cool. Sound good? Do I sound like I know what I'm talking about?
I was about to say, it's also great for convincing your computer science friends you know what they're doing.
You tell your computer science people that you know what they're doing.
I know what binary is.
Look at me, 0s and 1s, dang it. Okay. What we're gonna do now is draw those things. So this is harder, in my opinion, than reading off a diagram that's already done. Corey, we were just talking about you. Yeah, well, it was concern. It's like, has anybody seen Corey? Corey's had one class in this unit, and we're gonna have a test on Friday.
That's what the online lectures are for.
Oh, well, see.
I watched them.
I do have a note packet for you. I brought it last time. You weren't here. And I found some mistakes in it, so I actually printed some recovery pages for you too. But I didn't bring my stapler today, so you'll have to do this yourself later. But I didn't have my code right, so my bubbles, my little diagrams didn't show up in here. So these are the pages to replace these 4 pages in there.
Gracias.
Mm-hmm. Okay, so on 6 through 10, we're going to draw these finite state automata or steady state machines. Our language is 0s and 1s still, because computers, binary. Okay, so we're going to draw a machine that recognizes this 0, 0, x. X is any string.
Yes.
We just did this, yes. Do I have to draw it again, or can I just take this and... Although mine looks like I drew like a cat. That's pretty fun. Maybe I should draw it for you.
That looks like a bear.
Okay, fine, a bear.
Bears' ears are rounded. Cats are slim. That's how I've always, you know.
That's the difference between a bear and a cat. Just that. Good to know.
So if your cat ever has
So,
long shaped
for
ears, you better run.
my cat has really round ears.
She is a bear. My cat's ear's been cut off, so she's a feral cat, so she's been fixed. They mark them to know. She chose us. She chose our yard. She won't allow anyone but me to touch her. But she sleeps on our porch and stuff. She doesn't defend her territory though. I got her a little house to sleep in. She only sleeps in it when it's cold. When it's hot, she sleeps on all the furniture and gets hair on everything. But it's cold now, so she sleeps in her little house. But she was in there shivering, and so I put in like some old rags or whatever for her to like cuddle up in. Well, we had a different friend decide to cuddle up in her bed. When she was gone, I was like, could you not just defend yourself? This possum was like, and I walked out there to scare it off, but I was standing in front of the thing so it wouldn't come out. So I had to like pick up her house and shake her. Right. Well, I think she still counts as a feral cat because we can't get her to come inside. But okay. Sorry. This one we have an x, a 0, 0, and a y. So x and y are any strings of zeros and ones. Okay, so this is our start bubble. This is S0. With you. So I would like for if I pick up a 0 to move to the next one. I mean, I don't know. These are hard to like sort of do. Like I'm thinking I'm going to start with this and then we'll adjust. So I'm going to start with this and like say that's good enough. How do we feel about that? Right, so x and y are any strings, that means they could be empty, right? So 0, 0 would get me to that final state, that would be fine. Problem is I need to have zeros and ones coming in and out of every state, so how am I going to do that? S2 can have some ears. I can't make them pointy, so this will be a bear. You can do it as one arrow and put it with a comma, but I want to draw some ears. So the 1 could stay here, right? I'm missing a 1 coming out of S1. What do I do with that? Can it stay in S1? If I send it back to S0, then I don't have to trash that string because it could have 2 zeros that appear later, right? So, but if I send it back to S1 and it starts over there, or S0, I mean, and it starts over there, then it could eventually have the 2 zeros. So this one doesn't have a permanent trash place, right? It just has that the strings will they'll stop in a place before they can get to the final state. It doesn't have a place to dump things. Once it hits that 0, 0, then it's done and you've got it and we're good to go. If it never hits that 0, 0, you're going to stay in like this. In these two states, you'll just be stuck in them. You just start drawing and see. But like if this went to the trash, right? if I put this to the trash, I had 1, 0, 1, and then 0, 0. Well, that's a state that's a string that would be accepted because it ends with 2 zeros. And so I would have to figure out how to then go from there back to this state or make another final state. We're talking about this in a minute, but there are lots of ways to draw these things. Some are more concise than others, or in terms of like computer programming, they're going to be more efficient than others. So this one is the minimum number of states you would need to do this. You could draw a fourth state. If you draw a fourth one, you're probably going to have to draw a fifth one or get creative about how you leave that. Yeah. So there are lots of different ways to draw these diagrams. And yeah, but there is a like minimum, most efficient way, a minimum number of states you would need to do it too. Okay, on this one, interestingly, we are going to do the language consisting of the set of all strings that do not contain 2 consecutive zeros. So this one, I know I'm going to have a trash pile. That trash pile is going to be the strings with 2 consecutive zeros. So if I start this, and I have these 2 consecutive zeros here, then this is going to be my trash pile. And once I get to the trash, I'm not going to come out. But if I have just like some ones to start with, oh, cool. Thanks for that circle notability. What in the world?
I don't know, it's been a while since I've been in preschool.
My son is doing 3D shapes in first grade, so times they are a-changing. Oh, okay, that's not what we're going for. Okay, I'm tired of doing this. So if I start in S0 with some ones, I'm fine, right? If then a 0 appears, I am still fine. If a 1 comes after that, I should loop back. I can't loop in it because I got to be careful about double zeros. But if I loop back here with my 1s, then I'm okay. This is how I labeled this on my diagram, just so we know. My trash pile is death. Dark. Descriptive, helpful. Dark. Yeah, that's why it's so sad. Okay, but this is a precious smiley face with the other ear. Okay, so this would be it. Do you have questions? Do you feel good? Feel fine? This is hard, this next one, but I think y'all are ready. Do we feel okay about number 8? Ready to move on? Okay. Number 9. Are you using a colored pencil to take your notes? I love it. Was that intentional or is that just all you had?
Yeah, that was intentional.
I like it.
Yeah, in my earlier class, I was trying to color code, and I'm not really great at it, but we're getting practice.
Yeah. Writing in yellow is a risky choice, I feel like.
Oh, that's the highlighter color.
Oh.
Which I suppose is kind of redundant with other color pencils already. But
No, I know. I think it's great. I like it. Okay. The language consisting of the set of all strings that end with 3 1s. They end with 3 1s. Well, let's just pretend it's only 3 1s. And then we'll adjust from there. So we have a 1, 2, 3 ones. This is where we're going to start. This is where we're going to end up.
We have a 0, we set it back.
That's right. So if we start with a 0, we're going to stay here, right? If we have a 1 followed by a 0, we're going to send it back to start over. Go back to first base or whatever, right? Go back to the starting line. You false started there. If we get a 1 and a 1 and then a 0, well, okay. We're going to send it back also. But if it goes 1, 1, 1 and then a 0, we got to leave. So if I meant to draw a 0 here, sorry. If we get 1, 1, 1 and then a 0, then it can't stay in S3. It's got to leave. Because it wouldn't end in a 1, 1, 1. It would end in that 0 or whatever. We have just one ear. What if I make this ear the opposite ear?
It's got double chin.
Yeah, looks good. He's very happy. Okay, so we've got ending in 3 1s at least. If some 0s appear, that's fine. We got to start over to try to end in 3 1s. This as a like regular expression situation would be 0 or 1 star, and then a 1, 1, 1. Followed by a 1 star. Because you got to have the 3, but you could have more. Yeah. This is the ear. These are the 1, 1, 1. Okay. Good, bad, in between? We're good? Okay, the strings that contain at least 2 zeros. Just contain them. I don't care what order they happen in. So how do I do this?
So you progress, you get a 0 and you just stay the same if you have a 1.
Progress if you have a 0. Stay if you have a 1. What about that last state? What do I do with it? It's a final state, right? Okay.
Anything is acceptable now since it's
We want 2 years. Anything is acceptable now. All things are permissible, but not all things are beneficial. There's your faith integration for today. You're welcome. Course evaluations are open, speaking of. You can fill those out.
I can't see anything in mine.
Cool. That's helpful. Maybe someday. All right. Any questions about number 10? How would you write this as a regular expression? The language defined by what? How do you write this? The things that this program, this machine would accept. How do you write that? I have no idea. Maybe would work, not the most efficient.
1 star 0, 1 star 0, 0 star.
Yeah. 1 star, 0, 1 star, 0, 0, or 1 star. So 1 star keeps us in S0. We get a 0, we progress to S1. 1 star keeps us in S1. We get a 0, we progress to S2. And then once we're in S2, we can do any combination of zeros and ones. Good? All right. Y'all are doing a great job. So now we're going to look at machines that are already drawn. Oh, these two. This is what I was talking to Emily about a minute ago. So we are going to talk about the language recognized by this machine, and then we'll talk about the language recognized by the bottom one. So there are two final states on this diagram, this house diagram. Talk to me about what, to get to this final state, what do the strings look like? To get to this one, to S1, that final state, what do the strings look like? Just one. Okay, what if we want to get to this one? What do the strings look like? 1 0, some more zeros maybe, and then a 1, right? So 1 0, some more zeros, and then a 1. So this is our option. Option number 1 is take this road and, stop if it's only 1. If it's something else, you got to keep going, and you are going to end up not in the final state because we can't get down here. If we go this way to start with, that's fine. Zeros will keep you here. 1's going to take you to this final state. You don't want anything after that, or you leave and go to a trash pile. Okay, so this is the language recognized by this machine, and we're going to talk about this one down here as well. This has one final state in it. What does this look like? 0 star 1. That's it, right? Okay, do you believe that these are the same? They are. Because this will accept just a 1, so will that. Right? If it's not just a 1, it's got to have a 0 first. This would have that. So does that. Right? So the set of strings accepted by both of these machines are the same. Do you see that or not see that? Yeah.
The 0 star can be just 1 0 then, right?
It could be just 1. It can be none. If it was just 1, though, we're here. It's this none. This is our 1. So either it starts with a 1 or it doesn't, and it starts with a 0, at least 1 0. So any string that you could come up with that would be accepted up here would also be accepted down here. So these two machines are the same because this thing says up here that two finite state automata are the same, are equivalent if they recognize the same language. So these, both of these, the like regular expression would be 0 star 1. That's the language accepted by both, and that is so the machines are the same or equivalent. Obviously, they're not the same, but they are equivalent because they do the same thing, right? But if you were programming this, one of those is much more efficient to do than the other one. You have a lot of excess, like trash, in this one that your program has to store somewhere and deal with, right? You don't have that here. And so this is more efficient. That's what you want to go with. Does that make sense? Yeah? Okay. Then we get to do chapter 9, which is our last chapter of the semester. And it is no proofs, just counting and some probability. So, my least favorite section of the course. I do not enjoy this at all. I enjoy some of this. I don't enjoy like counting problems. I'm not a great counter. It's fine. There are three kinds of mathematicians: those who can count and those who can't. Yeah, I know.
I got it.
Good. Thanks. That's a joke for you. A math joke for you. It's what you needed today. Okay. So probability, yes, Dr. Greaves and I often have some discussions about statistics. So we are going to talk through some probability stuff, and then we'll do some counting. So, because you got to count to do probability. So tossing two coins, how many heads are showing? What are our options? 0, 1, or 2. All right, so a sample space, I meant to fill this in so you wouldn't have to, but that's okay. A sample space is the set of all possible outcomes of a random process or experiment. An event is a subset of the sample space. So S is some finite sample space which all outcomes are equally likely. And E is an event in the sample space S. Then the probability of E, denoted P of E, is the number of outcomes in E divided by the number of things in S. So you can also write that as the number of things in E over the number of things in S. That's the cardinality situation. Y'all remember this from when we did sets stuff? This is cardinality of E over the cardinality of S. Yes. Okay, so what's the probability of throwing one coin that has a head showing? Huh? I think just for one coin, just one half. We good with that? And then we got to figure out how many things are actually in S and how many things are in E if we're going to use more than one coin, right? We'll hold off on that. Okay. Alrighty then. For a standard deck of playing cards, standard deck has 52 cards, guys. These are facts about a deck of cards that I always have to teach people. 52 cards in a deck. "13 numbers, 13 types of cards. This is 1 through 10. Jack, queen, king, and an ace. 4 suits. Clubs, hearts, spades, diamonds. Oh, yeah. 2 through 10, my bad. 2 through 10. 4 suits, so one of each type in a suit. Because 13 times 4 is 52. Are we good? Alrighty. Standard deck of playing cards. What's the probability of drawing a black face card at random? So the probability of this event happening is equal to the number of black face cards divided by, the number of cards. So how many black face cards are there? Face cards would be the ones with people on them. So that is a jack, a queen, and a king. So there are 6 face cards in a 52 card deck. That's your probability. I don't care if you reduce things. We good? Any questions or comments so far? What's probability? What's probability when rolling a pair of dice that the sum of the numbers showing is 6? What? Not 3, but 5. Because the order matters. Yeah. So the probability of the event happening is the number of ways to get a 6. Divided by the number of pairs. So how do we do this? The ways to get a 6 would be a 1 and a 5, a 2 and a 4, a 3 and a 3, a 4 and a 2 and a 5 and a 1. Those count to 2, yeah. Because it's 2 different rolls that would give it to you, right? Dice number 1 is this, dice number 2 is this, yeah? Okay, so die number 1, die number 2. How many, so that's 1, 2, 3, 4, 5, right? How many pairs are there? In slot number 1, how many numbers could I have? 6. And slot number 2, also 6. So 6 times 6 is 36. Sorry, everyone. Somebody was showing me, like, if you fill this in with all the possibilities, there's 6 times 6, so that's how you get the 36 on the bottom. If that helps you think through why it's that. I do the counting thing, like I got 6 things here and 6 things here. They have to both happen, so that's 36 options. When you do this too, you can like see the there's like a diagonal of the things that add to 6, or there, you can make it that way. So anyway, that's kind of interesting. But there's your probability for number 2. Number 3, what's the probability that a randomly chosen 3-digit integer is divisible by 5? It is 1/5. How do we get that? Okay, 2 out of 10 possibilities. So 2 that are divisible by 5 out of 10 total. I'm getting that, the way that I'm thinking about this is it's a 3-digit number, right? For this 3-digit number to be divisible by 5, this is either a 0 or a 5. So that's 2 out of the 10 things that could go there, right? And the out of the 10 total is your probability is 1/5. Yeah. Okay, if m and n are integers, this is a counting situation, m is less than n, then there is n minus m plus 1 integers from n to n. Sorry. M less than or equal to n, there is n minus m plus 1 integers between the things. You got to subtract them and add 1 because you started on 1. So you got to count the fact that you started on 1. That's why there are 10 things here, like 10 total things here, because it's 0 through 9. So you do 9 minus 0 plus 1 to get the 10 possibilities to go in that spot. Does that make sense? But that's because 0 counts. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I can't raise my pinky finger too. 10, 9, 10, right? So you do 9 minus 0 plus 1 to get the fact that there should be 10 between 0 and 9 here. Is that okay? Yes or no? Hello?
Yes.
Good. Okay. That's going to be fun for all of you to listen to later, me beating on the thing. Okay. So we are first going to talk about possibility trees, and then we're going to talk about the multiplication rule. So a possibility tree is where you like have different choices depending on what happened in the step before your step, right? So like if I choose this, then it limits my options for my next choice. The multiplication rule is different. We'll talk about it in a second. So we have these two teams, A and B. They're going to play each other repeatedly until one team wins 2 games in a row or a total of 3 games. And then we're going to count probability, but we're going to do this first. So teams A and B are going to play each other repeatedly until one team wins 2 games in a row or 3 games total. So we have our first game here, right? So this is game number 1. Possible outcomes in game number 1 are that team A wins or team B wins. Yeah? So that's not going to work. I'm going to put the winning team on the bar. So A, B, team B wins. What happens from here? I got to choose a branch. Let's choose the A branch. Let's work it first, okay? So team A wins the first game. What happens in game 2? Team A wins or team B wins. So team A wins or team B wins. What happens if team A wins? It's over. Team A won 2 games in a row and we're done. I'm going to put a red dot on that to mark the end of that branch. Is that okay? Yes? All right, so let's suppose then that team B won the second game, not team A. What happens next? Team A wins or team B wins. If team B wins, what's happening? It's over. If team A wins, what happens? Not yet. They got to win 3 games total or 2 games in a row. No. A or B. If team A wins, it's over. If team B wins, they got to play again. And what happens on this branch? They're both over because that has been one of the teams will have won 3 games. Questions or comments about that? No? Okay, so we're done with this branch if A won the first game. What if B wins the first game? Then B wins the second game, say. It's over. If A wins the second game, it's not over, and they got to play again. What happens if team A wins that game? It's over. Well, I tried to make this symmetric, but I really botched it, so sorry about that, everyone. Okay, if team B wins, then it's over, right? They've won 2 games in a row. If team A wins, we got to play one more. But it's over then. Yeah? Okay. So how many different branches do we have here? It's 10. Are we counting that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 branches total. So that is 10 possibilities. So we're going to do the probability that 5 games are needed to determine a tournament winner. Boy, that's hard to say. So we want to know the number of things in the event, and we're going to divide by the number of things in the sample space. Well, there are 10 branches. So how many of these branches took 5 games to complete? 2 in each of the things, right? This, and this took 5 games. 1, 2, 3, 4, 5, right? 1, 2, 3, 4, and then the 5th one. So all 4 of these took 5 games to complete. So it is 4 out of 10, or 2/5 for that probability. Is that okay or not okay? We've lost confidence. Why? Oh, yeah, that is tedious. Yeah. That sort of thing is really hard to chase because you have to chase each branch and see what happens because the things are not independent of one another. But when you have something that is independent, so I'm going to give you an example here. This is kind of what I was talking about earlier. Like, let's say that I'm going to Cup of Mana to order coffee from Emily. This is me. Okay, I'm going to go order some coffee, and first I've got to make a decision if I want hot or iced coffee. Okay, so do I want my drink to be hot or do I want my drink to be iced? Okay, and then from there, I need to decide, do I want a coffee drink, an espresso drink, or tea? Yeah? So do I want coffee, espresso, or tea? Yes? Coffee, the choice is the same down here, coffee, espresso, or tea. I should have drawn these further apart because now I'm going to run into some issues. Here, let's just scoot you away from there. Oh, okay. Now from here, I want to decide, do I want, for some reason, Cup of Mana has decided not to have non-fat milk. So I can't get skim milk. I can get almond milk, oat milk, or 2% milk. So I can do almond, oat, or 2%. Almond, oat, 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 2%. Yeah? Okay, so in my first, set of choices, how many choices could I make? Just 2, right? At that next step, how many choices did I have? Once I chose hot or iced, I had 3 choices. Oops, that's not a pencil. And then in my last step, how many choices did I have? 3 milk choices. So total branches here should be 18. 3 times 3 times 2. Let's see if it is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So when the steps are independent of one another, if you have the same choices after you make the first choice, then this is the multiplication rule. So this is different than this one up here because once team A won one, if they won the next one, we were done, right? And so you could make the same kind of argument, let's say, about this, but anyway. So the multiplication rule is that the number of steps or branches isn't dependent on the previous step. That's not stated well, and I'm sorry. But like step 1 is N1 possible outcomes, right? Choices. Step 2 is N2 choices. Step K, all the way down to step K, is N sub K choices. So the possibilities, total possibilities, this is what this last line is for, can be performed in N1 times N2 times N3 times N sub K ways. So that's how many branches, how many possibilities that there are, how many branches you could be on is just a product of all of those things. This is how like Sonic, Sonic is like the drink I don't know why I looked at Eunice. She does not know. Sonic was like the drink destination or whatever, and they were like, you can try this many kinds of drinks. Well, it's because they get to multiply all of those things. Like, no, you're probably not going to put coffee and, I don't know, blue coconut or whatever in your same drink, like, but you could, right? So they get to name the possibilities, but because they get to multiply everything, so the number gets really big, so it's like nice and catchy to say, right? But in all likelihood, people are not doing that. Okay, so if A, B, and C are sets with D, N, and M elements, how many things are in the set A cross B cross C? We talked about this when we did cardinality, because you're picking off something from each of the sets. This is our first little bit of counting. I have been ordered triple. Yeah? That's what would be an A cross B cross C. Y'all with me? Elements in A cross B cross C are ordered triples, where this is in A, this is in B, and this is in C. You with me? Okay, so how many possibilities do I have to go in blank? 1. D. There are D things that could possibly be in blank number 1. How many things could go in blank number 2? N. And how many things in blank number 3? M. So the number of things in A cross B cross C is D times N times M. This is the multiplication rule. Thoughts? It's okay? All right, let's keep going. Okay, so we have the standard 26-letter alphabet, English alphabet, and 10 digits. How many 4-symbol pins can be formed using those things? Repetition is allowed. I need a 4-symbol pin, right? Yeah, it's 36 to the 4th. There are 36 things that can go in each spot, so this is 36 to the 4th. It's 36 times 36 times 36, because all have to happen. So it's D times N times M, right? What if we're not allowed to repeat? So I have this 4-symbol pin, but I can't repeat. Like if I've used an A, I can't use an A again. 36, 35. Well, now I've used an A and a B, and I can't use that A or B again. So 36 times 35 times 34 times 33. What's the probability that a pin chosen at random has no repeated symbol? So this would be the number of things in the event divided by the number of things in the sample space. So this would be the number without a repeated symbol divided by the number with possible repeated symbols, right? Yeah. So it's going to be our last two problems. So repetition not allowed is 36 times 35 times 34 times 33 options. Repetition allowed is not 36 factorial, 36 to the fourth. So that would be the probability on that one. All right, any questions about that? No? No. Okay. A permutation of a set of objects is an ordering of the objects in a row. So if I put these things in an order, I put them in a row, right? A permutation of these objects is a reordering of them. Yes? But this is when you create a list and order does matter. I need this, so just pretend I didn't put that in that list. So if I have these, I need more things. I have these 5 things. How many permutations, how many ways could I order those things? It is 5 factorial. Why? You said 5, 4, 3, 2, 1. Yeah? Didn't you?
I said 5 times. Up to the fifth.
Oh.
It's 5 factorial because.
Because I couldn't have repeats. So 5 to the 5th,
Oh, that's true.
right? But it is 5 factorial. Why?
Because they're starting position.
So this, if I choose the phone to go in the first spot, I have 5 choices for the first spot, right? I choose it. How many choices do I have for the second spot? 4 now, right? How many choices do I have then for this third spot?
3.
Yeah. How many choices do I have for the fourth spot? And now for the fifth spot? 1. So the number of ways to do this is 5 factorial. Are we good? Okay. For an integer n with n greater than or equal to 1, the number of permutations of a set with n elements is n factorial. So we just did that with a 5. And R permutation of a set of n elements is an ordered selection of R elements taken from the full set of n elements. So the number of R permutations, that is really confusing, but we're going to talk about our example just a second ago. So this says you have a total of n elements. You're going to make a list of R of them. How many possibilities do you have? Right? So we have 36 symbols. We're going to make a 4-digit pin, a 4-symbol pin. Yeah? So that is P36-4. We are permuting 4 of the 36 possible symbols. And we want to know how many ways we can do that. Well, I have, because, you know, I'm not repeating, I have 35 times 34, 36 times 35 times 34 times 33. Okay. So this in a like formal setting, like definition wise, permuting an R permutation of n elements is going to be n factorial divided by n minus r factorial. So thinking back to our example, P36-4, right? We already know that this is this thing, but let's see if we can get it using this formula. So this is our n, this is our r. So we're looking at 36 factorial divided by 36 minus 4 factorial. 36 factorial, that would be divided then by 32 factorial. Everybody with me? Well, that's 36 times 35 times 34 times 33 times 32 times 31 and so on. Oh my gosh. And then on the bottom, we're looking at 32 times 31 times 30, whatever. These are going to cancel out with all of those, and we're left with just this guy, which is the same as this. Yeah? So the formula works. You can count it by hand. If the numbers are bigger, you're not going to want to do that. So this formula is how you would get that. Does that make sense to all of you? Okay. So let's talk through this. How many ways are there to award first, second, and third place in a race with 12 contestants? So I want to know how many ways can I award first, second, and third place? Does the order matter? Yes, because first place is better, right? Order matters here. So we're going to make a list, which is going to be a permutation. 12, 11, 10, right? It's that product. 12 times 11 times 10. I don't know what that is. Doesn't matter. But this you could get from the, this is P12-3. You have first, second, and third places. So you're permuting 3 of the 12 elements. You with me? This is going to be 12 factorial over 9 factorial, which is just going to be 12 times 11 times 10. Good? Yes? How many ways can you arrange 5 people in line for a picture? It is 5 factorial. Yeah? We just did that one a minute ago. That's my bad. I spoiled it. Or my items here. We had 5, 4, 3, 2, 1 items. How many arrangements of the letters A, B, C, D, E, F, G, H contain the string ABC? I think it's 6 factorial. So I have 1 item, 2, 3, 4, 5, 6 items, right? So I have 6 things, so that is 6 factorial. This works with the, oh, I should talk about this, sorry. This is P6-6. You're permuting all 6 of the elements. With that formula, this is 6 factorial over 6 minus 6 factorial. So that's a 0 factorial on the bottom, which annoyingly enough in math is a 1. Because why not? Because we can. How many pages we got left? Can we just stop there for today? You think? I only have a couple minutes, but I don't think we should start a new section. Nah. Okay. We've done 9192. That's great. We'll do 9395 on Monday. You'll have a test on Friday. We'll cover this on Monday. Test on Friday. Yes. You didn't watch class from the other day, did you, Eunice? Do you have a test on Friday? Differential equations? Okay, we'll work that out. We decided since your final was supposed to be on Saturday, but got moved to Wednesday, that you taking a test on Monday and then a final on Wednesday didn't work. So we're going to take it Friday, and then I'll get them back to you on Monday. We'll figure out when you can take it. Okay. Yes, it is. Y'all have a wonderful Thanksgiving. You're going to turn in homework 13. Oh, Corey, I have that for you too. You're going to turn in homework 13 Monday when